So today we're going to start digging into atomic structure and how it relates to the structure of the periodic table. If you know the way the periodic table is arranged, how it's set up, what it means by the positions of all the elements in the structure of the table, you can write the electronic structure of the element very easily. So let's carry on. See, I got my marker. Yep. What we know about the universe, in fact, not just chemistry, but the vast majority of information that comes to us about the whole universe comes to us through light, electromagnetic radiation. We've been out in our nearby neighborhood with actually with feet on the ground and with mostly robotic explorers, and have managed to sample some of the universe. A limited number of those samplings were returned to Earth for analysis. Most of them, if there was any analysis done in these remote locations, the information was transmitted to us by light. So we need to find out what light is all about. It gives us clues as to what's happening inside the atom. So let's look at, well, colors. We recognize light based upon the colors that we see. But that's not the whole story. It's a beginning, right? Why do we have colors? Why do some substances emit colors or absorb certain colors? Fireworks will emit colors. They're designed to do that. And we change the color of the explosion by the element that's incorporated in the package. Here's Elijah. The easiest colors to produce in fireworks are yellows and oranges. Reds are a little more difficult. Blues are extremely difficult to produce. But it is possible. I see some right in here. Why do they make those colors? What is it about the chemical reaction, actually, that occurs in a fireworks explosion that makes those colors? Well, different chemicals give different colors, and we're interested right now in, for the moment, in elements, how the elements emit colors when they're excited, that is, when they're heated. So if we introduce different elements into these flames, we get different colors. Right? Zinc is a bright yellow, calcium is kind of an orange, sodium is more an orange-red. Potassium is kind of a, I don't know what you call that, hot pink. And barium is blue. Now these colors also vary with the temperature. So if you change the temperature of these flames, you will slightly change the color. Right? So hang on to that idea for a while. It has to do with the amount of energy that we're pumping into the atom before it releases that energy back to us in the form of light. So these elements, if we put them in solution or in a different compound and go into solution, into aqueous solution, we get different colors. So there's something else going on there besides just the individual element emitting light. Now, you can also get colors from compounds. And in particular, I'm thinking about organic compounds. When you look at leaves through the summer, most of them appear green. Some of them have kind of a reddish color. I've got a Crimson King maple in my backyard that's mostly red or deep dark. reddish color. But most plants that you see, grasses, trees, are going to be green. And they're green because of the compound chlorophyll. And there's so much chlorophyll in there, it sort of swamps out the other colors. So you only see the yellows and the oranges and the reds and those other colors in the fall when the chlorophyll starts to break down and the plant is heading toward dormancy for the winter. But those colors are produced by organic compounds, and the structure of those compounds dictates what color you will see. Now, there's a difference between what we saw earlier here with the flames. Those are due to emission. They actually emit those colors. They're coming from the elements in that flame. The kind I'm talking about with chlorophyll and those other colors, the xanthophylls and the anthocyanins that are contained in leaves, those are absorption colors. Even spell. It's a B. They're due to absorption. The light that strikes them or is passed through the leaf is absorbed on its way. And anything left over is the color you see. So the green from chlorophyll is a color that chlorophyll does not absorb. It absorbs on the red end and the blue end of the spectrum. And that may not mean anything right now, but I'll explain it in a second. But it's leftover color, the absorptions. But that can give us information about the compounds and the chemicals. What colors do they not absorb? Red blood cells, they're red because of hemoglobin. And not just hemoglobin, but it has to be oxygenated. Hemoglobin is a compound protein with 4 iron atoms embedded in it. They're chelated. In other words, the molecule is set up so that chela means claw in Greek. So they claw that iron and hold it there. And the iron reacts with oxygen, and that transports oxygen through your blood to the tissues. But it's only red because of that combination of iron and oxygen. I grew up in Georgia, and the soils down there, most of them are red. That's because of the high content of iron oxide in the soil. If it doesn't have the oxygen, it's kind of a purplish color. So venous blood will be that color until it strikes the air and then starts picking up oxygen. Then it turns red. Okay, I did my master's thesis on crawfish processing waste. So the crawfish, the live crawfish, come into the plant, they boil them, and then they peel them and package the tail meat to distribute all over the country, all over the world actually, and just freeze it. But the shells are reddish color, and they're red because of this compound. And you don't have to remember that compound. It's just the fact that you can get different colors, not just by the element, but by the structure of the molecule as well. You'll notice that all these double bonds in here, right? Those are singles, these are doubles. The double bonds, every other bond is a double. And that is called conjugation. If they're within one single bond of each other, they sort of share an environment for their electrons. And the number of them that you have and the way they're organized in the molecule determines what color it is. You have some of these that are like carrots, that beta carotene, vitamin A. They're more orange, not so much red, but they're actually half of that molecule is the source of the beta carotene. And it's simply because there are not as many of these double bonds, it absorbs and emits in different wavelengths. Okay, enough said about that. Let's characterize light. We don't just want to say this color or that color. We need to be quantitative with our description of light. And we have 3 terms that, in combination, describe light. I'm going to start at the bottom. Speed of light. It's very fast. The speed of light in a vacuum is 2.9979 times 10 to the 8th meters per second. It's really fast. Now, it varies depending on whether it's moving through a vacuum or it's moving through a transparent object. Right? It does interact with matter. But for now, we're going to speak of it in terms of that speed in a vacuum is constant. Then we have frequency and wavelength, and those two are related. Wavelength, think of light as a sine wave. That. So it's moving in this direction, and it's varying both in its electrical field strength and its magnetic field strength, which is neither here nor there for our purposes. But the wavelength is the distance between two crests. And we use a small lambda. That's the Greek letter lambda, stands for wavelength. And this distance between those two crests is in units of meters. Those are standard SI units. There's another unit that we use, and I'll talk about it in a minute. Now, frequency is if you fix your gaze on this point, how many of these crests pass your eyeball in 1 second? So how many cycles pass this point in 1 second? Okay, so the units of measure for frequency, which sometimes I see it a small f for frequency, but I learned it in terms of that Greek letter, which is nu, nu. Looks like a V, but it's really a nu. It stands for frequency. Okay, so frequency is in terms of cycles per second. But since cycles is not a unit of measure, cycles just, how many things happen. The units for this is reciprocal seconds. Seconds to the -1, or 1 divided by seconds. Now, in honor of one of the giants of the study of light and signal transmission using light, Hertz. That's also equal to 1 Hertz. 1 cycle per second, 1 reciprocal second is 1 Hertz. But unless all your measurements in a calculation are in Hertz, then you can't cancel. So if you need to cancel, if you need to combine terms, units of measure, you should use reciprocal seconds. Okay, now how are they related? Well, the speed of light is given the symbol c, and its units are meters per second. Okay? It is equal to the wavelength times the frequency. The wavelength is in meters, frequency is in reciprocal seconds. So meters per second. I like to look at the units of measure just to see, make sure that they're not pulling my leg. So at least the units match. So we know that this one is 2.9979 times 10 to the 8th meters per second. That means since this is a constant, then if this one goes up, that one has to go down. Or if this one goes down, that one has to go up in value in order to make this one constant. So they're inversely related, these two. The longer wavelengths, as this one gets bigger, longer wavelength means, let's see. Well, this is reciprocal seconds. Let's look at it in pictorial form. I think that would make more sense, rather than my trying to describe it. Okay, there are your terms and their equivalents They're all related through this formula. Now, when we look at the representation, like I was trying to do here, we see that this one has a wavelength here, a certain wavelength, and we're saying that its frequency is 4 cycles per second, or 4 hertz. So notice as we go down, we're shortening the wavelength, which means we're increasing the frequency. Frequency is 4 hertz here, but it's 8 hertz here because the wavelength is shorter. Right? More waves pass a point in 1 second with this one, with a shorter wavelength, than they did with this one. And this one is even twice as fast as that. Okay, so that just illustrates the inverse proportion. Right? As the wavelength decreases, the frequency increases. Okay, electromagnetic spectrum. This is everything we know about light, all the representatives of light. It goes from this end, which is the very shortest wavelengths, gamma rays, all the way up to the longest wavelengths, radio waves. And radio waves can be tens of kilometers long. It can be very long distance between wave crests. But we talked about colors in the beginning. The color, the spectrum that we can see, the visible spectrum, is very narrow, extremely narrow. Most of the electromagnetic spectrum is not visible to the human eye. But now we have instruments that can detect these wavelengths, actually use them, and we can tune to pick up, to determine what wavelength we're actually receiving or emitting. We do that all the time with our radios. When I was a kid, you had to do it manually and turn a dial. Right? Now, of course, you punch in a number and electronics do it for you. Okay, so if we start here, the longer wavelengths is the red end, and the shorter wavelength is the blue and violet end. Right? As a kid growing up, we learned the colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. RGB. That other unit of measure I was mentioning. If we look at the measurement in terms of meters, we find that the red end is 7 times 10 to the minus 7 meters wavelength. But that's difficult to deal with. I mean, it's kind of like in a conversation, I wouldn't want to say 7 times 10 to the minus 7 meter. It's too much trouble. So we use a different measure. So 7 times 10 to the minus 7, is it? Meters. We're going to change that to a new unit. Right, meters. We're going to use nanometers. So 1 nanometer is a billionth of a meter. So 1 nanometer is 10 to the minus 9 meters. Okay? So if we divide this one into this one becomes positive, and that one is 7 times 10 squared nanometers, or 700 nanometers. Knowing that now, the visible spectrum runs from 400 nanometers to 700 nanometers. That's a little easier to deal with. Okay, so if we move to the longer wavelengths, we come to infrared, right? And if you ever go to a fast food restaurant and you have to wait for your food, they probably, well, actually any restaurant, that when the cook finishes your food, puts it up on the ledge for the waitress or the waiter, and there's a red lamp above it. It's a heat lamp. That heat lamp is tuned to emit infrared radiation. because infrared radiation is more efficiently absorbed by your food, keeps it warm. We use infrared detection, our military does, to see the enemy at night, because our warm bodies emit infrared radiation, and at night everything else is a lot colder, so they just stand out like, you know, big bright targets. Microwaves are the next longest part of the spectrum. We use microwaves for a number of things, but commonly we use them to heat our food. And the reason we use microwaves is one particular wavelength of microwave radiation is absorbed very efficiently by water molecules. Most of our food has water in it. So we just bombard it with those waves. The water molecules pick up that energy, and right, we conserve energy. You can't destroy it, can't create it. But once it hits that water, then it converts that light energy into vibration and heat, and transfers that heat by conduction throughout the food. That's why if you have food that's, it only penetrates a certain depth in your food. So if you try to heat it too fast, the outside will become too hot, even dried out, before the inside gets warm. So that's why when you heat up something that's really thick, you want to reduce the power. So that's why you have power setting on your microwave. You say, all right, instead of 3 minutes at high power, 100% power, I'll make it 20 minutes at maybe 20% power. And that gives it time to heat all the way through the food. Anyway, microwaves are used for that. They're also used for information transfer. You used to see a lot more than you did do now, is these towers out here, not cell phone towers, but microwave towers. So they would be up there, and they would have directional antennas, and they would beam their signal from here miles away to another tower, and then downlink on microwaves. We listen to the radio, FM, AM. Ham radio operators use shortwave. This is their region. Okay. They use shortwave because of the way these longer wavelengths travel great distances. They even go over the horizon. How do they do that? Because the light beam goes straight and it doesn't curve. So what it does is the shortwave radio in particular, here's the Earth, and radiation from the sun and particles from the sun strike the Earth's atmosphere, and our magnetic field directs them around us so that we don't get bombarded with stuff. But while the solar wind is moving its way around the Earth, it ionizes molecules up here. Atoms and molecules in the upper atmosphere, produces a layer called the ionosphere. Well, the ionosphere is very good at reflecting these long wavelengths. So if you got a tower down here that's broadcasting a signal, it'll strike that ionosphere and be reflected down to a receiver. So over the horizon is possible with that, with the longer wavelengths. As a kid at night, when there was less interference, no sun up, I could pick up Chicago and Tennessee. And now, when I drive to Logan on Friday mornings, it's still dark, and I get too far from Beckley, I can't pick up any local stations. So I tune to 7:50 a.m. in Atlanta. Pick it up. I mean, it's not very interesting. It's news, weather, traffic reports at that time of the morning, but it's something in the background. Okay, on the other end of the spectrum, past the violet end, we get ultraviolet. And now we're getting into radiation that can penetrate and damage cells. So when you get a suntan in the summer, if that's what you like to do, what you're doing is you're damaging your skin. And your skin's response is to produce more melanin to protect you. So over time, if you get too much of that, you'll actually damage the nuclear material in the cells, and there's always a chance that they'll turn cancerous. X-rays, right? We've used X-rays for forever to look at the inside of bodies. Actually, we use them to look at other materials too. When pipelines are being built, there's probably a stipulation in the contract that every well has to be X-rayed for cracks, for imperfections. And they have to keep those records in case there's an accident, then they can prove that it wasn't their fault. But X-rays, now, when we get X-rays in the dentist office or we think we've broken a bone, the potential damage from X-rays is much, much reduced. Originally, massive amounts of X-ray energy had to be bombarded. Your body had to be penetrated by large amounts because the film was so inefficient, right? To pick up the image on the other side with poor film, you need large doses to get there. But now, very, very low dose X-rays will give them good images because we have electronic detectors on the other side picking it up. Gamma rays. I will say, and I'm going to explain why in just a minute. As you go from this end of the spectrum, long wavelength to the short wavelength, these wavelengths are carrying with them higher and higher amounts of energy. So these are low energy end to the very, very highest energy end of the gamma rays. Now, astronomically speaking, there are phenomena that occur in our galaxy and other galaxies called gamma ray bursts. They are massive releases of energy in this region of the spectrum. Fortunately, they're very directional. That is, we can see them, but we only see scattering from them. And that's a good thing, because if one of these gamma ray bursts was directed at Earth, right, if it happened however many light years ago, and it intersects us in our orbit, then it will strip the Earth of its atmosphere. They're that powerful. Right? It's what's known as an ELE, an extinction level event. So very, very powerful gamma rays. We do get gamma rays also in smaller amounts from nuclear decay. Radioactive elements will sometimes emit gamma rays when they decay, but those are in small amounts. Okay, so that's the electromagnetic spectrum. What's the point of this slide? What we're emphasizing here is that energy is convertible. You've got electrical energy, direct current coming through these leads, and it's being transmitted through that pickle because it has lots of vinegar in it, right? It has acid in it, which gives it ions to transfer the current, but it's very high resistance. So when you put high voltage into this pickle, you heat it up and it glows. Now, a lot of that energy is converted into heat. I wouldn't be a bit surprised if this were an animation. If we could see this in a video, you'd see steam coming off that pickle. But it also creates light. And the point is that when you energize a molecule by adding energy to it, in this case, electrical energy, it can give up that energy in various forms. And one of those forms is it converts it into light. Now that concept is used by astronomers to deduce the temperature of stars. They treat stars as black bodies. They don't make any of their own energy, we know they do. But on the surface, there are no nuclear reactions. So all the energy is being supplied from inside. So by the time it reaches the surface and starts to excite those surface atoms and molecules and ions and whatever, that plasma, then it starts to emit colors of light, radiation. And it's proportional, it's directly proportional to the temperature. The higher the temperature, the bluer the star. So really cool stars by comparison are reddish. That's known as black body radiation. Okay. Historically, the description of light was quantified in a series of equations by James Clerk Maxwell. And he published these equations in the middle 19th century, and they described the behavior of light perfectly for what they understood and knew about light at that time. There's some things they didn't know about light that were going to come back to bite them after they thought. The thinking was, that's it. We've solved all the mysteries of the universe. We might as well pack up and go home. Now, under certain circumstances, these equations are still valid. That's if we treat light as a wave. Right? We've only described it at this point as a wave. That. But there are certain behaviors of light that look more like particles, like electrons, for instance. And when that happens, along comes different theories. Right? If the bodies in the universe, and these are related to classical physics, classical mechanics, and wave physics. But when bodies get really huge, like black hole size, then all of our classical physics breaks apart. It's no good anymore. So we have to resort to general relativity. And Einstein is getting credit for that one. And when we get really, really, really small, they break down there too. These equations don't work when you get small. So that's where quantum mechanics comes in. And I made that statement before. Scientists thought that we know everything. We just sit back and watch the universe go, tinker around. Okay, I mentioned black body radiation. Max Planck, who was, I think he was Danish, in 1900, was studying black body radiation. And he noticed the relationship between the energy that light could transmit and the frequency of light. So there's a relationship there. They're proportional. The higher the frequency, the higher the energy of the light. Okay? You notice that relationship. Well, this is not an equivalence. It's not an equation. So he recognized the relationship there first. Now he needed we call it a proportionality constant. Another word for that is fudge factor. So he fudged it with a constant that we now call Planck's constant. So the purpose of the constant is to make the units of measure behave. Right? This is in reciprocal seconds, right? This is in joules, energy. So this one has to be in terms of joules, seconds, right? That way, this second cancels that second, and you're left with joules. And then there's a number that accompanies that unit. And I think it's in here somewhere. There it is. 6.626 times 10 to the minus third minus 34 joule seconds is Planck's constant. And that's in your useful information. You don't have to memorize it. I don't even have to memorize it. So let me go back. What Planck was saying was that the amount of energy is so dependent upon the frequency of light that at a given frequency, that light beam only can deliver this amount of energy. It's quantized. In other words, there's nothing in between. Maxwell's equation says light energy is continuous, right? And there's no break. It's from a continuum here to there. But Planck was saying that light is delivered in packets. Now we're starting to talk particles, not continuous waves. And the fur started to fly because every scientist worth his salt knew that light was waves. That was it. But now we're seeing physical evidence that light is not wave only. In some circumstances, it behaves like a particle. So at the beginning of the 20th century, that was the raging debate. Is light a wave or is light a particle? Well, the short answer is yes. It's both. They had to agree that it was both because the developing theories and the equations that were based upon either wave function or particle function, they're both valid under certain circumstances. And they couldn't resolve the difference. So they just had to say, all right, it's both. Just pick the one we need, depending on the circumstances. Okay. So now that we know how to determine the energy of that packet of light, which we call a photon, let's see. Oh, I got a video.
Everybody knows Albert Einstein for his theory of relativity and the Nobel Prize he won for it. He also— What? I didn't win the Nobel Prize for relativity. I won it for explaining the photoelectric effect. Right, of course, sorry. Einstein won the Nobel Prize for his work on the photoelectric effect, which helped settle the age-old debate of what light is made of. So, what is it? Okay, let's rewind a little. Newton had thought light was made of particles, and his rival Hooke had thought it was a wave. And when technology advanced enough, some experiments proved Hooke was right. That proof, and Maxwell's equations describing light's behavior as a wave, made the debate die down, until the photoelectric effect was discovered. When light hits a cable next to another cable, electrons jump from one to the other. It was thought it happened because waves of light made atoms vibrate until they ejected an electron. But when it was measured carefully, a big contradiction was found. It only happened for light of some wavelengths. For others, no electrons jumped at all. Einstein was bewildered. The photoelectric effect should work regardless of the type of light. If light wasn't made of particles, and now it turned out that it couldn't be made of waves, what was it made of? After much reflection, he formulated a new hypothesis combining the two previous ones. What if light were made not of waves or particles, but of both? That is, what if light were made of wave packets? That concept, which we now call photons, allowed Einstein to write out equations that explain the photoelectric effect in 1905. This consolidated the idea that light can sometimes be described as a wave, sometimes as a particle, and sometimes as either. It was a revolutionary view, and it opened the field for quantum physics. Robert A. Millikan, an American experimental physicist, was unconvinced by Einstein's conclusions, so he set out to prove him wrong by carefully measuring the photoelectric effect. However, years later, Millikan ended up proving Einstein right, and they were both awarded the Nobel Prize in Physics.
So, Einstein was a theoretical physicist. He had never set foot in a laboratory. He did all of his scientific work up here. And he had plenty of time to do it. He was a patent clerk, reviewing patents for the Swiss government in Bern, Switzerland. And he was extremely intelligent. He could review all the patents that he was given for that day in a couple hours. And then the rest of the day, he could just sit and daydream, which he did a lot of. So he formulated explanations for the photoelectric effect. And then when Robert Millikan got hold of it, he's a crack experimental scientist. Remember him from the mass of the electron. He determined that with his oil drop experiment. But he also tried to disprove Einstein, and it turned out that actually proved it. So that's why they both got the Nobel Prize, but for the same phenomenon, but for different reasons. Okay, anyway, the photoelectric effect. It is, in short, the ability of light of a certain wavelength to eject an electron from the surface of a substance. And most often we use metals, because metals, they like to give up their electrons anyway in a chemical reaction, so they're more likely to eject an electron. But it doesn't have to be a metal. We use photovoltaic cells. Their basis is silicon, which is, at best, we could describe silicon as a metalloid. But we dope the silicon in such a way that it responds to light and ejects an electron picked up by another part of the circuit, and then that's shunted off as current. Anyway, so this photoelectric effect, when we have the material and light strikes that material, it has a certain amount of energy. And if it's sufficient energy, it will eject an electron. Okay? It will free that electron from the atoms in the material. So there's a minimum amount of energy required, right? This E0 is the minimum. This is called the work function. Which is simply the frequency or the wavelength of light that will deliver enough energy to eject an electron from the surface. And now when the electron is ejected, it's free from the atoms underneath, but it has no energy of its own to travel anywhere. It's just sitting right there. That's why it's the minimum amount of energy. If the light, and if we increase the frequency or shorten the wavelength, we increase the amount of energy available. But it only needs this much energy to get loose. So where does the rest of the energy go? It's translated into kinetic energy. So any excess energy, if this is the total energy supplied by our light, then it only needs this much, right? It only needs that much to get free. And then the rest of it is converted into, kinetic energy. Right? So now it's off and running like that. So the shorter the wavelength, once you reach the work function, the shorter the wavelength, the more energy you supply, and the faster these electrons move when they leave the surface. Okay? If the frequency is too long, is too small, then there's not enough energy, and you will see no electrons at all. Now, what Maxwell's equations should have done was predict that if we increase the intensity of the light at the same wavelength, right? We're not changing the wavelength, we're making the light stronger. Then Maxwell's equations predicted that at a certain intensity, you'd start ejecting electrons. But doesn't happen. It's only when you shorten the wavelength and increase the energy of the photon that you start to eject electrons. So when you increase intensity, you're actually throwing more photons at the surface, each one with sufficient energy to eject an electron. So if you do that, then the more intense light beam will simply eject more electrons. Okay? So up to a certain point, no electrons. Beyond that, you get some electrons, more intensity, you get more electrons. So in electrical terms, when you eject more electrons, you get a higher current, because current is measured in charge passing a certain point per second. So you get more current with more intensity, but you don't get electrons ejected unless you meet that minimum frequency. Okay, that's the photoelectric effect. Let's see. Well, these are conclusions that I've already given. There's another name for those photons that don't have enough energy. They are absorbed by the material. So we've got to do something with that energy. We can't create it, we can't destroy it. Right? So it turns into heat. So those are called thermal photons. Right? If their frequency is not high enough to eject an electron, then the material just absorbs the energy. All right. So I got a couple of minutes. Let me see. How far do I want to go with this? What does the photoelectric effect tell us about the structure of the atom? Okay, now we're getting to the whole meat of the subject. Because if light is delivered in packets, then when we eject electrons, the electrons respond to that packet because of the way they are structured around the atom. When light interacts with matter, it's actually interacting with the electrons. It doesn't have any influence or impact on the nucleus, just the electrons. And when a photon of light is absorbed, then the electron is promoted from a position closer to the nucleus to a position further away. So when we look at an atom, we have a nucleus here with its protons, and then we have an electron here. If light energy approaches of a certain energy, if it's the right amount of energy, then that electron will be promoted to the next energy level. It doesn't just go up here in this space. It can only go from here to here. Or it can go to a higher energy level if the energy is sufficient. Right? So this quantized energy allows us to predict the movement of electrons to energy levels. That's my alarm. Okay. Let me see. This would be a good place to stop. I don't really have a choice.